Okay, let's talk about the representations of motion lab. Now, understanding these graphs and describing the motion can be pretty tricky. So if you didn't do so well on your first attempt, that's okay, don't worry about it. You're in physics to learn, and I'm here to help you learn. So let's talk through it. I want to start out by talking about the coordinate system. So if we were doing this for real in person, we would have a motion sensor device. It's a little device that emits ultrasound, and that ultrasound bounces off the objects you're looking at. And based on the time delay for that rebound, that echo of the sound to return the motion sensor, it can calculate how far away it is. So that's like echolocation. That's like how bats and dolphins and other animals can do echolocation. So the coordinate system that we use is that you have increasing position as you move away from the sensor. Right? If you're right next to the sensor, that's 0 position, and as you move away from it, that's increasing position, increasing x. What this means for velocity is that when you move away from the sensor, that's positive velocity. Remember, that's because velocity is change in position over time. And if you move away, your change is positive. If you move toward the sensor, that is negative velocity. Because the change in position is negative. When you get closer, that change is negative. Now, we can't really say anything about the sign of acceleration until we get to the particular cases, because acceleration is change in velocity, so it depends on whether you're speeding up or slowing down and moving toward or moving away. So we'll talk about that when we get to some examples. So let's just start with that warm-up example on page 7 that they did for you, but I'll go through it and explain it with you too. All right, so for all of these we have a description and 3 graphs. And we want to fill out all 4 of those things, description plus 3 graphs. So in this one, in this example, we have a description. It says move toward the sensor at constant speed. And we've got our 3 graphs: position versus time, velocity versus time, acceleration versus time. Now, based on this description, the easiest graph to fill out first would be the velocity versus time graph. We know that if you move toward the sensor, that would be a negative velocity. And if we're moving at constant speed, that means the magnitude of the velocity doesn't change. So that would be a constant negative value, or a horizontal line that's negative. And here they give you some values. They say it's -2 meters per second. Now from our definition of acceleration, well, let me remind you of these definitions. Velocity is defined as change in position over time, and acceleration is change in velocity over time. So if we have a constant velocity that's not changing, that means that acceleration is 0. So for this example, we would have 0 acceleration. It would just be on the horizontal axis the whole time at 0. And now we can think about position versus time. If you move toward the detector, that means your position is decreasing. You start out farther away and you get closer. And because we're moving at constant speed, that means it's going to look like a straight line with a slope of -2. So the position versus time graph will be like that. All right, so let's do these other parts. To redraw that one. Okay, so this is part B, question B. And we are given just the position versus time graph. So we're given its position, it's at 2 meters, and it's a horizontal line. So what does that mean? Well, this means that you're standing 2 meters away from the detector and you don't move. Your position doesn't change. That's pretty simple motion. It's not really motion at all, you're just standing there. So if you were just standing stationary in place, by the definition of velocity, your velocity is 0. And if your velocity is this constant 0 value, then by the definition of acceleration, your acceleration is also 0. So question B is pretty simple. Let's move on to part C. In part C, we're also given just the position graph. And it looks like, make this a little bit bigger. It looks like it goes from 2 to 4 over the course of a few seconds. Just they kind of label some times here. These graphs are very roughly labeled. It's okay if we don't get these numerical values exactly correct. Those are seconds. Okay, so what's happening here? Well, we start 2 meters away from the motion sensor, and then we move away from it. And you can tell that because this line is straight, we must be moving at a constant speed. So the description is start 2 meters from the detector. And move away at a constant speed. So constant speed implies that your velocity versus time graph is a horizontal line. And moving away implies that your velocity is positive. So velocity versus time is going to look like that. So this velocity is constant. You're moving at a constant speed in the positive direction. Because this velocity does not change, that means acceleration is 0. All right, so that was part C. Part D looks pretty similar, but you start a little closer to the detector and end up the same distance away in the same amount of time. So this time you start pretty close to the detector and end up the same distance away. So this is almost the same motion, except you have to move faster to travel that greater distance in the same amount of time. So it's a lot like part C. You start close to the detector and move away. And you're moving at a constant speed, which you know because this is a straight line. So your velocity versus time graph is a horizontal straight line. It's just a larger value than in part C. It's a greater speed. It's still positive because you're moving away. And your acceleration versus time is still 0 because this velocity is a constant value, not changing. Okay, let's do part F. What did they give you in part F? Just the velocity graph this time. So in part F, we start out with this. This velocity starts at 0, it increases, and it's positive the whole time. Because it's positive the whole time, it means you're moving away from the detector during this whole motion. And because it's getting bigger, it means you get faster and faster as you move away. So this motion could be, maybe you start 1 meter from the detector and you start moving away, and then you get faster and faster and faster as you do that. Let me do that again and watch where I'm going. So you start close to the detector and you start moving away and then get faster. That's what this velocity versus time is telling you. Now, because acceleration is the change in velocity over time, or the slope of this line, acceleration is a constant positive value. It's some constant number that equals the slope of that velocity graph. Remember, we talked about this relationship between acceleration and velocity vectors. When the two vectors point in the same direction, then an object speeds up. So in this scenario, we're speeding up. We know the velocity is positive. That must mean that the acceleration is also positive. All right, so let's make the position graph. Now, we don't know where the object starts. In fact, it's arbitrary. It could start at any position, and as long as you keep moving away at increasing speed, this will work. So I'm just going to pick a random point to start at and draw my position graph. Now, because of calculus reasons, if velocity is a straight line, then position is going to look like a parabola. And that's just something you can remember for now. All right, so our description of this motion is you start close to the detector, close to the detector, and move away with increasing speed. That sums up all these graphs. Now I want to do part G, give you a head start on the next assignment, and we'll talk about the other parts next week. All right, part G, they give you the position versus time graph, and it looks like this. So you can see that you start far away, and as time goes on, you get closer. The position decreases. So you must be moving toward the sensor. And if you look at how this graph is changing, at the beginning, it's changing a lot. Toward the end, it doesn't change very much. That means that you start walking toward the sensor fast and then slow down as you get closer to it. So let's describe this motion. You're walking toward the detector with decreasing speed. You're slowing down as you do so. Now, with that description in mind, we're going to draw the velocity graph. This whole time we're walking toward the sensor. That means the velocity must be negative the whole time. So whatever graph we draw, it has to be below this horizontal axis. The other fact we know is that you start out fast and get slower. So we need to start out with a large negative velocity and end up with a small negative velocity. And the third fact is this is a parabola, so velocity is going to be a straight line. We can sum all that up with a graph that looks like this. It's negative the whole time. This whole graph is below 0. It has a large speed to begin with, and as you move toward the detector, that speed gets smaller, it gets closer to 0, but stays negative the entire time. All right, now here's where you're really going to get confused when we talk about the acceleration. Acceleration is the slope of the velocity graph. That slope is positive. So this acceleration is positive. Let's think about what that means. Remember we said that when acceleration and velocity point in the same direction, that means you speed up. When acceleration and velocity point in opposite directions, you slow down. So in this example, you're slowing down. Your velocity vector is pointing toward the detector. So you start out fast and you get slower and slower. Because you're slowing down, that must mean that the acceleration vector points opposite the direction you're going. You're going toward the detector, that's negative in this coordinate system. So opposite that is positive in that coordinate system. That's why acceleration is a positive value. All right. Ponder those concepts. I know this is tricky to understand, and certainly the rest of the examples in this lab are going to be even more difficult. Do the best you can, and we'll talk about the rest of them next week.